Okay, today we have the exciting opportunity to learn about exponential functions and E. Now, our upcoming unit that we're studying about is all about exponential functions and logarithm functions. Now, we gave a little bit of an introduction into those two different things, but exponentials and logarithms are inverses of each other, exactly like what we were talking about in our last unit. So when it comes to inverse functions, that means they undo one another. Now, there are lots of different pieces to exponential functions and inverses and those logarithms. But really what we're going to focus on today is mostly on some exponential functions as well as the number e. Now the number e, just for a little bit of reference, is actually a number similar to pi. It is irrational just like pi, but it obviously isn't equal to the same thing. Now e is short for Euler's number. And it comes from the mathematician Euler, who was able to investigate and figure out what it equals. Now, approximately Euler's number equals 2.71828, and it has a lot of interesting applications. It actually comes from doing the summation of 1 over n factorial from 0 to infinity. So it is kind of a mathy, cute thing there. But what we're going to be exploring today is exponential functions. We're actually specifically going to be talking about an application of exponential functions called compound interest, which, in case you may or may not know, is all about money. So we are going to be talking a little bit about money today, and we'll talk about compound interest. But first, we'll investigate a little bit of compound interest. We'll talk about where e comes from and things like that. Now, just as a review of exponential functions are written in this form. Typically, what considers something to be exponential is because the exponent is a variable. Okay, so if it has an exponent as a variable, that is what makes it an exponential function. Then from there, what you can see is they have some interesting properties. So if we wanted to graph the function where b is bigger than 1, right? So if we had something like 2 to the power of x, you're going to see that it goes up when a is positive. If we had negative 2 to the power of x, it's going to go down, right? Following that same pattern. Now, when b is between 0 and 1, so we see something like 1/2 to the power of x, then all of a sudden we're going to get a pattern where it is exponentially decreasing when it's positive, and when it's negative, that gap is also decreasing here. So when you hear these different things, a lot of the time when you see something like this, people are talking about something called exponential growth, because as the x value gets bigger, the y value also gets bigger. This is considered exponential decay, because as the x value gets bigger, the y value gets smaller. And not only does it get smaller, but the distance from the previous y value to the next one is also getting smaller and smaller. So that proportion is reducing there. Now, when it comes to an example of what these graphs look like, we kind of talked about it. To the power of x is going to be one that looks like this. If you wanted to find exactly those points, you could go ahead and put in different values. So if I started by putting in x equals 0, anything to the power of 0 is just 1. If I started putting in those negative values, remember that ends up writing it as a fraction. So we would get 1/2 and 1/4. To the power of 1 would obviously be 2, and 2 to the power of 1 is 4. So you can kind of see how they start small and all of a sudden get bigger. A big thing to note here is that they do have a horizontal asymptote at 0, right? So regardless of what number I put in here, however negative of a number, it's impossible for an exponential with a positive base to become negative. Okay, when it has this fractional, so between 0 and 1 for our base here, what ends up happening is we end up getting this exponential decay. The reason why is as we go to look at it in that XY table there, we're looking at this power of 1/2. So if I have a -2, -1, 0, 1, 2, just like we did before, 1/2 to the power of 0 is obviously 1. 1/2 to the power of 1 is 1/2. 1/2 to the power of 2 is 1/4. 1/2 to the power of -1 is actually 2, and -2 is actually 4. So it has us kind of reverse that property there, as you can see. So what we're going to do is explore a little bit more about the application of these. So a very specific, very exciting and cool way that we can see an application of exponential functions in the real world is from compound interest. Now, there are lots of different types of compound interest. Compounding interest means that as you invest money, what happens is they calculate interest over time, whatever specified amount of time, and that interest will then accumulate on there. So if I started by investing $100 and after 10 days, they were going to do a 1% interest, then all of a sudden at the day 11, I would have $101. So then 10 days later, when they go to calculate 1% interest again, what would happen is they do 1% of my $101. So I'd get $1.01, right? So then all of a sudden I'd have 102 and a cent. And you can kind of see how that builds and builds upon itself. Now there are formulas and there are equations that we can kind of look at here. So compound interest is just going up. We see it in the real world all the time. A lot of the time when people are investing money, we'll see an idea of compound interest. You also can see some calculations of relating to this interest when it comes to things like population growth. There's also that direct relationship between other things there. Now, what I would like you to do next is go ahead and pause this video. We are going to turn and watch another video from one of my favorite mathematicians of all time. His name is Eddie Wu. If you've never heard of him before, I would 10 out of 10 recommend checking him out. Eddie Wu is a mathematics teacher in Australia. He's got kind of a cool story. His TED Talk is the best. I would totally recommend checking it out. But for right now, what we're going to do is we are going to be watching him talk about what is the number E and where does it come from? And he's going to relate it directly back to compound interest. So with that being said, if you are watching this video on your own, go ahead and pause it. If you're watching it as a class, again, go ahead and pause it. And I want you to go to this video by Eddie Wu and watch it. He is teaching this lesson to a live class, so you will hear kids in the background making comments and things like that. But go ahead and enjoy where that comes from there. Okay, now that you have finished watching that other video, let's go back and talk a little bit more about compound interest. Now, Eddie Wu talked about compounding things. And when we compound things, there's different ways to compound it. If we were to compound something yearly, you would end up using this equation. So A is the amount of money that we end up earning. P is called the principal amount or the initial amount that I put in there. So what I put in is kind of what I'd like to think of with that P. R is our rate of interest in the form of a decimal. So for example, if it's 8% interest, we would put it in as 0.08, right? Now in this example, he used 100% interest, and that sounds kind of crazy, but he did talk about it in terms of like reproduction with things like animals or humans or something like that. If two humans have two kids, that's 100% interest, right? So you can kind of see that connection. T is our time invested. So we would end up using a formula that looked something like this. So for example, if I had $5,000 or $500, let's say, and I was investing it at a rate of 8% for the next 15 years, right? What I could do is I could calculate how much money I would have at the end by taking my $500, multiplying it by 1 plus our 0.08, raised to the power of how much time we've done that. And as we go through and use our calculators to calculate that quantity there, what we end up getting is something along the lines of 1.08 to the power of 15. We end up getting something like this, 1,586.08. Okay, so if we invested $500 and left it there for 15 years and didn't touch it, we would almost triple the amount. Now, where these numbers come into play here is this one right here is coming in by saying, regardless of what happens, what that interest is, you will definitely get at least $500 back out. Then you'll get this increased amount as we go on. Now, Eddie Wu started by talking about yearly, but then he started talking about what happens if we do it more often than once a year. Now, you do have the option of compounding something yearly or compounding something monthly or quarterly or annually or things like that. So N just represents the number of times per year. Everything else is consistent there. So you can see that we end up dividing that rate by the number of times per year, and we end up putting that in there. Now, what happens is there are some common ones that you'll end up seeing when you see semi-annually. What that means is you are doing it twice a year. If you see quarterly, we are doing it 4 times a year. If you are doing it monthly, because there are, oh, that's not how you spell month. Monthly, because there are 12 months in a year, we would use 12 for our N. If you were doing it daily, right? We could do it 365 days a year. You watched as Eddie Wu continued on to do it more and more times, right? But the same formula applies here. So P is still our principal amount, things like that. So say we were looking at compounding $500, just like we did last time. We're still going to do it at 8% interest. We're still going to invest it for 15 years, but this time it's going to be compounded monthly. So let's take a look at how this changes our value. So last time we ended up getting a quantity of $1,586.08. If I compound it monthly, what's going to happen is we'll use our new formula of 500 times 1 plus 0.08 divided by the number of times per year, which is 12 times 12 to the power of 15. Now I'm going to go ahead and type this into my calculator here. I would challenge you to do the same. So we do our 500 times 1 plus 0.08 over 12 to the power of 12 times 15. And what we end up getting here is you end up getting 1,653.46. Okay, so now take a look at that. Just increasing the amount that we've compounded it, all of a sudden, we're now making, right? So as you look at this, we go from 1,586 to 1,653. So all of a sudden, we are making $67.37 just on the opportunity of compounding it more often. I didn't have to change my finances. I didn't have to do anything else. Now, a lot of the time, things like that will happen. Now, you can compound it as much as whatever you're investing it in will allow you to. But when it comes to this mathematical statement, they have something that's called compounding it continuously. And that's where E comes in. Now, we saw Eddie Wu explain kind of where that number comes from. And as we increase the number of times that we're compounding, if we do it with a principal interest of 1, we'll notice that that number in nature approaches the number E. So what happens here is if we're continuously compounding it, so they're using that calculation over and over and over again, we end up using this formula. So let's take our same situation there. We've got our $500 that we're investing. We're still investing at 8%. We're still leaving in for 15 years, but this time we're going to compound it continuously. So what we'll see is this ends up being that maximum amount because there's no way that we can compound it more often than that. So we take our 500 times E to the power of 0.08 15. And as we go to calculate that, if you're looking for the E button ever, it is able to be found right above the natural log button. It looks like it says IN, but it's actually an LN. As we end up doing this here, we end up getting the quantity of $1,660 and about 6 cents. So this is going to be that maximum amount if they're compounding it continuously under those conditions. But you can see how even then we ended up making almost $7 more than we had the time before that. So we can see how this compounded interest can be super awesome. So what we are going to have you do after this is just practice. But if you have any questions, don't hesitate to ask. But that's kind of how we go through and we compound with each of those. So there are the 3 different equations here that you'll need to know. The one if we're compounding yearly, the one if we're compounding mid-year. Now just know if you do decide to do it yearly, you can still use this formula here because N will just become 1 and it'll all of a sudden turn into that other formula, right? So you totally can just use this one if you need one to remember, but we also have this compounding continuously. So anytime you see that continuous, this is the one you'll use. If you have any questions, don't hesitate to ask, but that is compound interest and E and a little bit of where it comes from and one way that we can use it in the real world by taking our money, investing it, and doing something else with it.